Before you sleep tonight, let's take a journey together. Not a journey of miles or kilometers, but something much larger. We're going to explore the distances between stars, the spaces between galaxies, the vast quiet emptiness that fills most of the universe. This isn't a race. We're not trying to get anywhere quickly. Instead, we're going to move slowly through ideas that help us understand our place in the cosmos. Ideas about light years, what they measure, why they matter, how they connect distance and time in ways that seem almost magical. Along the way, you might find yourself drifting. That's perfectly fine. This exploration is designed to be restful, meditative, calming. Some nights, understanding cosmic distances helps us feel peaceful about our own small corner of existence. The universe is vast, and you're safely here, about to learn something beautiful. Before we can understand distances measured in light years, we need to start with distances we already know. Our minds are built to understand the spaces we move through every day. Think about the distance from where you are right now to your kitchen. You know that distance intimately. You've walked it hundreds or thousands of times. Your body knows how many steps it takes, how long the journey feels, what you'll pass along the way. Perhaps there's a doorway you navigate, a corner you turn, a particular floorboard that creaks underfoot. The distance is so familiar it's almost unconscious. Your body could navigate it in the dark, or consider the walk to a nearby park. Perhaps it's 15 minutes on foot. You know the route without thinking. You know the tree at the corner where you sometimes pause, the crosswalk halfway there where you wait for the light, the bench where you sometimes rest, the smell of the flowers in that garden you pass in spring. The distance is concrete in your mind because you've experienced it with your body in all seasons, in different moods, at different times of day. These everyday distances make sense to us. A kilometre, for instance, is roughly the distance most people can walk in about 12 minutes at a comfortable pace. It's a measurement that connects directly to human experience. When someone says something is 3 kilometres away, you immediately have a sense of what that means. Not just as a number, but as an experience. How long it would take to walk there, whether you'd need water for the journey, whether you'd arrive slightly out of breath or perfectly comfortable, whether it's close enough to walk on a whim or far enough that you'd need to plan for it. This is how our ancestors thought about distance for thousands upon thousands of years. How far can we walk before nightfall? How many days' journey to the next village? How far can we see from this hilltop? How long until we reach water? Distance was always tied to experience, to the movement of our bodies through space, to time passing as we travelled, to the physical sensation of covering ground. A day's walk might be 20 to 30 kilometres, depending on the terrain, the weather, how much you're carrying. Our ancestors knew this distance intimately. They knew what it felt like in their legs, in their breathing, in their feet by day's end. They knew how the landscape would change over such a distance. They knew whether they'd need to camp or whether they'd reach the next settlement. Even when we moved beyond walking, the distances remained human-scaled. A day's ride on horseback might cover 50 to 80 kilometres. A week's journey by ship across the Mediterranean might take you from Greece to Egypt, perhaps 800 kilometres. 2 hours by car might take you from one city to another, covering 200 kilometres of highways and bridges and landscape. We measure distance not just in units, but in the experience of crossing that distance. The journey itself becomes the measure. You don't think of visiting your grandmother as travelling 120 kilometres. You think of it as a drive that takes about an hour and a half, where you see the old barn with a red roof, where you stop at that roadside stand in summer for fresh fruit, where the road curves through those hills you've always found beautiful. The distance between cities still makes sense to us this way. New York to Boston is about 350 kilometers. You can drive it in roughly 4 hours depending on traffic. You can picture the journey, leaving the dense urban landscape of New York, moving through Connecticut with its smaller cities and wooded areas, crossing into Massachusetts, finally arriving in Boston. The journey has stages, landmarks, a progression. It's a distance you can comprehend not just mathematically, but experientially. Even larger distances remain somewhat graspable when they're connected to something we know. The width of the United States from the Atlantic to the Pacific is roughly 4,000 kilometers. That's a 5-hour flight if you travel by air, watching time zones slip by beneath you. Or it's several days of driving, a classic American road trip where you see the country change gradually, from the dense forests of the East Coast to the expansive plains of the Midwest, to the dramatic mountains and deserts of the West. People make this journey regularly. It's long, certainly, it's an undertaking, but it's within the realm of human experience. You can imagine making that trip. You can picture the changing landscapes, the different cities, the gradual shift in climate and terrain. You can imagine the feeling of progress as you move across the continent day after day, the landscape transforming around you. Our planet itself is about 40,000 kilometers around at the equator. That's a large number, certainly. But we have context for it. Ships have circumnavigated the globe since Magellan's expedition in the 1500s. We know it's possible to travel this distance, even if it takes months. Modern aircraft can fly around the world in about 45 hours of actual flight time, though you'd need multiple connecting flights, and the journey would take several days, including stops. The Earth is big from our perspective, standing on its surface. Mountains seem enormous, oceans seem vast. Continents seem impossibly large when you're travelling across them step by step. But the Earth is a knowable size. It's finite. It's complete. You could, in theory, explore it all. People have walked across continents, sailed across oceans, climbed the highest peaks. The Earth is large, but it's comprehensible. All of these distances work well with familiar units: kilometers, miles, meters, feet. They all serve us perfectly for describing the world we inhabit, the world we move through, the world we can touch and see and experience directly. These measurements emerged from human experience. A foot is about the length of a human foot. A meter is roughly the length of a human stride. These are human-scaled measurements for a human-scaled world. But something begins to change when we look up. When we turn our gaze from the horizontal world we walk through to the vertical realm of the sky. When we start thinking not about distances across the Earth's surface, but distances into space. The moon hangs in our night sky, clearly visible, its features distinguishable even to the naked eye. On a clear night you can see the dark and light patches on its surface. With binoculars, you can see its craters, its maria, the dark plains that early astronomers mistook for seas, giving them poetic names like the Sea of Tranquility, the Ocean of Storms. You can see the rays of bright material spreading out from some craters, ejected billions of years ago by ancient impacts. The moon feels close, doesn't it? It's right there in the sky. Close enough to see details, close enough that it seems almost touchable. When the moon is full and bright, it casts shadows on Earth. You can walk outside on a moonlit night and see your surroundings clearly without any other light source. The moon is our companion, our closest celestial neighbour, always there, cycling through its phases month after month. The moon is approximately 384,000 kilometers from Earth. Let's pause with that number for a moment. 384,000 kilometers. It's easy to write, it's easy to say. But what does it mean? Can you picture it? Can you feel it in any intuitive way? Try to imagine driving 384,000 kilometers. At highway speeds of about 100 kilometers per hour, driving constantly without stopping, it would take you about 4,000 hours. That's more than 160 days of continuous driving, more than 5 months of never stopping, never sleeping, just driving endlessly through space if there were a road to follow. Of course, there is no road to the moon. There's no air to breathe along the way, no rest stops, no landmarks to mark your progress. It's just distance, pure distance across the vacuum of space. The Apollo missions of the 1960s and 70s carried humans to the moon. These missions required some of the most powerful rockets ever constructed. The Saturn V rocket that launched the Apollo mission stood 110 meters tall and weighed nearly 3,000 metric tons at launch, most of that weight being fuel. It burned enormous quantities of rocket fuel to achieve the speeds necessary to escape Earth's gravity and travel to the moon. The Apollo spacecraft reached speeds of about 11 kilometers per second during their journey. That's about 40,000 kilometers per hour. To put this in perspective, that's roughly 400 times faster than highway driving. Imagine traveling at 400 times the speed of a car on a freeway. Faster than sound. Faster than anything you've ever experienced. Faster than any commercial aircraft. In fact, the Apollo spacecraft were traveling about 30 times faster than a typical commercial jet. And even at that tremendous velocity, the journey to the moon took about 3 days. 3 days of continuous travel through the vacuum of space, moving faster than any human had ever moved before just to reach our nearest celestial neighbor. The astronauts would look out their window and watch Earth gradually shrinking behind them, becoming smaller and smaller until it was just a blue marble hanging in the darkness. They'd watch the moon gradually growing larger ahead of them, its craters and mountains becoming more distinct as they approached. For 3 days they travelled through space, 3 days of being farther from home than any human had been before. 3 days of watching the profound darkness between Earth and Moon, seeing both worlds hanging in space, understanding the distance between them in a way that no calculation could convey. Think about what 3 days means. 3 days is how long it takes to enjoy a weekend getaway. 3 days is 72 hours, 4,320 minutes, 259,200 seconds. For 3 days, moving at 40,000 kilometers per hour, the Apollo astronauts crossed the gulf between Earth and Moon. And this is just to reach the Moon, the closest celestial body to Earth, a neighbor we can see clearly in the sky, a world that feels, visually, almost touchable. When we start talking about the distance to other objects in our solar system, to the other planets, to the Sun, our familiar measurements begin to show their inadequacy even more clearly. Part 3. The Sun and the Inner Solar System. The Sun sits at the center of our solar system, about 150 million kilometers from Earth. We see it every day. It's so present, so immediate, so essential to our existence that we take it for granted. It rises each morning, crosses the sky, sets each evening. It provides all our light, all our warmth, all the energy that drives weather and climate and life itself. This sun feels close because we see it so clearly, because we feel its warmth on our skin, because our days are defined by its presence or absence. But 150 million kilometers is a distance that has no human reference point whatsoever. If you could somehow drive a car to the sun, maintaining highway speed constantly without stopping, it would take you about 170 years to arrive. You'd need to start the journey as a young person, and you'd die of old age many decades before reaching your destination. Your children would die of old age without reaching it. Your grandchildren might live to see the sun approached if they dedicated their entire lives to this impossible road trip. The fastest spacecraft humanity has ever built is the Parker Solar Probe, launched in 2018 to study the sun up close. It uses the gravity of Venus to gradually accelerate itself, swinging past Venus multiple times to gain speed. At its fastest, during close approaches to the sun, the Parker Solar Probe reaches speeds of about 192 kilometers per second. 192 kilometers per second. That's almost 700,000 kilometers per hour. At that speed, you could travel from New York to Los Angeles in about 20 seconds. You could circle the Earth's equator in just over 3 minutes. It's a speed that's almost impossible to comprehend, because nothing in our everyday experience moves anywhere close to that fast. And yet, even at this incredible speed, the Parker Solar Probe still takes months to complete its orbits around the Sun. The distance is simply that vast. Let's think about what 150 million kilometers means in terms of light, because this is where we begin to approach the concept of the light year. Light travels at about 300,000 kilometers per second. It's the fastest thing in the universe. Nothing can travel faster, and light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. 8 minutes and 20 seconds. When you look at the Sun in the sky, you're seeing it as it was 8 minutes and 20 seconds ago. That's how long it took the light to travel from the Sun's surface to your eye. The Sun you're seeing is the past Sun. If something happened on the Sun right now, if it suddenly dimmed or brightened or changed colour, you wouldn't know for more than 8 minutes. You'd continue seeing the Sun as it was, not as it is, until the light carrying that new information reached Earth. This delay creates interesting implications. When solar astronomers observe a solar flare erupting on the Sun's surface, that flare actually happened 8 minutes earlier. By the time they're watching it through their telescopes, it's already over. They're watching history, not the present moment. The planets of our inner solar system are all within a few 100 million kilometers of the Sun. Mercury, the closest planet to the Sun, orbits at an average distance of about 58 million kilometers, about 3 light minutes. Venus orbits at about 108 million kilometers, roughly 6 light minutes. Mars, the next planet out from Earth, orbits at about 228 million kilometers, about 12.5 light minutes at its average distance. But the distance between Earth and Mars varies dramatically as both planets orbit the Sun. When Earth and Mars are on the same side of the Sun, at their closest approach, they can be as near as about 55 million kilometers, roughly 3 light minutes. When they're on opposite sides of the Sun, at their farthest separation, they're about 400 million kilometers apart, about 22 light minutes. This varying distance creates practical challenges for space exploration. When NASA operates rovers on Mars, there's always a communication delay because of the time it takes radio signals to travel between Earth and Mars. Radio signals, like light, travel at 300,000 kilometers per second. When Mars is at its closest to Earth, commands sent from mission control take about 3 minutes to reach the rover. When Mars is at its farthest, those same commands take about 22 minutes. Any data the rover sends back takes the same amount of time to return to Earth. This means you can't drive a rover on Mars in real time like you'd control a remote-controlled car on Earth. If you tried to steer the rover remotely with immediate reactions, you'd be responding to information that's already several minutes old. By the time your command reached the rover, the situation would have changed. the rover might have already crashed into an obstacle or gotten stuck. Instead, NASA engineers must carefully plan the rover's activities. They analyze images from the previous day, study the terrain, plan a safe route, write a sequence of commands, and send those commands to Mars. Then they wait. If something goes wrong, if the rover encounters an unexpected obstacle or a system fails, they can't react instantly. They have to wait for the information about the problem to travel back to Earth, which takes 3 to 22 minutes. Then, they have to analyze what went wrong, figure out a solution, write new commands, send those commands, and wait another 3 to 22 minutes for them to arrive at Mars. A problem that might take seconds to solve with a remote-controlled car on Earth can take an hour or more to solve on Mars. The distance, though measured in mere light minutes, creates a fundamental barrier to real-time interaction. Part 4. The Outer Solar System and Beyond. Beyond Mars, the distances grow even more extreme. Jupiter, the largest planet in our solar system, orbits at about 778 million kilometers from the Sun, about 43 light minutes. Saturn, with its magnificent rings, orbits at about 1.4 billion kilometers, about 79 light minutes, or about 1 1/3 light hours. When the Cassini spacecraft orbited Saturn from 2004 to 2017, capturing stunning images of the planet and its moons, there was more than an hour of delay each way for communications. Engineers couldn't control Cassini in real time at all. They had to program entire sequences of commands days or weeks in advance, upload them to the spacecraft, and trust that Cassini would execute them correctly. Cassini had to be autonomous enough to handle problems on its own. If its instruments detected something unexpected, if a system began to fail, the spacecraft needed to recognize the issue and switch to a safe mode without waiting for instructions from Earth. Because by the time a problem was reported back to Earth and new commands were sent, more than 2 hours would have passed. In space operations, 2 hours can mean the difference between a minor glitch and a catastrophic failure. Uranus orbits at about 2.9 billion kilometers from the Sun, about 2 hours and 40 minutes at light speed. Neptune, the farthest planet, orbits at about 4.5 billion kilometers, about 4 hours and 10 minutes at light speed. The Voyager 2 spacecraft, which visited both of these distant worlds in the 1980s, had to be almost entirely autonomous during its encounters because the communication delays were so long. And beyond Neptune, we encounter the Kuiper Belt, a region of icy objects extending far beyond the planets. Pluto, once considered the 9th planet and now classified as a dwarf planet, orbits at an average distance of about 5.9 billion kilometers, about 5.5 light hours from the Sun. When the New Horizons spacecraft flew past Pluto in July 2015, it was about 5.5 light hours from Earth. The spacecraft had been programmed months in advance with every maneuver it would make during the encounter. During those few critical hours when it was closest to Pluto, New Horizons was completely on its own. Mission Control was receiving data about where the spacecraft had been 5.5 hours earlier. They were essentially watching history, not the present moment. All of this is still within what we consider our solar system. All of these distances from Mercury to Neptune to Pluto and beyond, these are our local neighborhood. These are the worlds that orbit our Sun, held by its gravity, illuminated by its light. And we haven't even left the neighborhood yet. Voyager 1, launched in 1977, is currently the most distant human-made object from Earth. It visited Jupiter in 1979 and Saturn in 1980, then continued outward into space. For nearly 50 years it has been travelling away from the Sun at about 17 kilometers per second. roughly 61,000 kilometers per hour. At this speed, Voyager 1 could travel from New York to Los Angeles in about 7 minutes. It could circle the Earth's equator in about 40 minutes. It's moving faster than any spacecraft that's ever traveled farther from Earth. Nothing we've built has gone farther or faster into deep space. And after nearly 50 years of constant travel through the vacuum of space, moving at 61,000 kilometers per hour with nothing to slow it down, Voyager 1 is currently about 24 billion kilometers from Earth. That's about 24 light hours away. One light day is about 26 billion kilometers, so Voyager 1 hasn't even traveled one full light day from Earth yet. One light day after nearly 50 years. This begins to give you a sense of just how large the distances become when we use light as our measuring stick. Voyager 1 is currently in what we call interstellar space, the region beyond the direct influence of our Sun, where the solar wind mingles with the thin gas that fills the space between stars. It crossed this boundary, called the heliopause, in 2012. It was a historic moment, the first human-made object to leave the heliosphere and enter the space between stars, but it's still, in cosmic terms, right here in our neighborhood, one light day, 24 light hours, after nearly 50 years of travel. Part 5. The Nature of Light. To truly understand the light year, we need to pause and consider light itself. What is light? Why does it have a speed at all? And why is that speed so important to how we measure the universe? Light is electromagnetic radiation. It's composed of photons, tiny packets of energy that have no mass but carry momentum and energy. Light exhibits both wave-like and particle-like properties, one of the strange quirks of quantum mechanics. But for our purposes, what matters most is that light travels. It moves through space, and it does so at a finite speed. For most of human history, people assumed light traveled instantaneously. You open your eyes, and you see. You light a candle, and the room illuminates. There's no perceptible delay. So it seemed natural to assume that light simply appeared wherever you needed to see it, that vision was instantaneous. The first person to seriously challenge this idea was the Danish astronomer Ole Rømer in 1676. He was studying the moons of Jupiter, carefully timing when they disappeared behind the planet during their orbits. He noticed something peculiar. The eclipses didn't happen at exactly the predicted times. When Earth was closer to Jupiter in its orbit, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Rømer realized what was happening. The eclipses were occurring at regular intervals, exactly as predicted. But the light from those eclipses had to travel across the changing distance between Earth and Jupiter. When Earth was closer, the light arrived sooner. When Earth was farther, it took longer. The eclipses weren't happening at different times. The light was taking different amounts of time to reach Earth. This was a revolutionary insight. Light had a speed. It wasn't instantaneous. It traveled across space at a finite velocity, and that travel took time. Rømer calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite accurate because he didn't know the exact size of Earth's orbit. But he had proven the fundamental point. Light travels at a finite speed. Over the next few centuries, physicists refined this measurement. They used increasingly sophisticated methods, rotating mirrors, precise timings, interferometry. By the late 1800s, measurements of the speed of light had become quite accurate, and in the 20th century, with the advent of lasers and atomic clocks, we measured the speed of light with extraordinary precision. Light travels at exactly 299,792,158 meters per second in a vacuum. For most purposes, we round this to about 300,000 kilometers per second. This is one of the most precisely known constants in physics. We've confirmed it through countless experiments and observations. It's always the same, regardless of where or when you measure it, and this constancy is crucial. According to Einstein's theory of special relativity, developed in 1905, the speed of light is the same for all observers, regardless of how fast they're moving. This seems impossible at first. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the ground sees the ball moving at 150 kilometers per hour, the speeds add. But light doesn't work this way. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you don't see the light moving away from you at half light speed. You see it moving at exactly light speed, and someone watching from outside also sees it moving at exactly light speed, not at 1.5 times light speed. This seems impossible because it contradicts our everyday experience, but it's been proven true through countless experiments. The only way this can work is if space and time themselves are flexible, adjusting to keep the speed of light constant for all observers. If you're moving very fast, time literally runs slower for you, and distances in your direction of motion contract. These aren't optical illusions or measurement errors, they're real physical effects. The speed of light isn't just fast, it's special. It's the cosmic speed limit, the maximum speed at which any information or influence can travel through space. Nothing with mass can reach light speed because doing so would require infinite energy, which is impossible. The universe doesn't contain infinite energy. Only massless particles like photons can travel at light speed, and they must always travel at light speed. They can't slow down or speed up. From the moment they're created to the moment they're absorbed, photons travel at exactly the speed of light. It's simply what photons do. It's their nature. This fundamental speed limit has profound implications. It means that cause and effect are limited by the speed of light. If something happens on the sun, the effects of that event can't reach Earth faster than light can travel, which is 8 minutes and 20 seconds. If a star explodes 20 light years away, we can't know about it for 20 years. The speed of light creates a cosmic speed limit not just for matter and energy, but for information itself. Nothing can communicate faster than light. No signal, no influence, no cause and effect can propagate faster than 300,000 kilometers per second. This is why the light year works so well as a unit of measurement. It's based on a universal constant that's the same everywhere in the universe. It's based on the maximum speed at which anything can travel. And it inherently connects distance with time, reminding us that in the cosmos, where something is and when we observe it are inseparably linked. Part 6. Defining the light year. Now we can define the light year properly, with full understanding of what it represents. A light year is the distance that light travels in 1 year. It's not a measure of time, despite having year in its name. It's a measure of distance. The year tells us the duration of travel, but what we're measuring is the distance covered during that travel. Let's calculate this carefully. Light travels at approximately 300,000 kilometers per second. That's the starting point. Now we need to figure out how far light travels if it maintains this speed for an entire year. There are 60 seconds in a minute, so in 1 minute light travels 300,000 x 60, 18,000 kilometers, 18 million kilometers in 1 minute. There are 60 minutes in an hour, so in 1 hour light travels 18,000 x 60, 1 to 180,000 kilometers, more than 1 billion kilometers in 1 hour. There are 24 hours in a day, so in 1 day, light travels 80,000 x 24, 25,920,000 kilometers, about 26 billion kilometers in 1 day. There are 365 days in a year, So in 1 year, light travels 25,000 or 27,000 x 365, so there's us 9,000 or 60,000, 800,000 kilometers. That's 9.46 trillion kilometers, nearly 10 trillion kilometers. Let's write that out. 9 times 4 for 60,000, 800,000 kilometers. Or we could write it as 946 x 1012 kilometers in scientific notation. This is what 1 light year represents. The distance light travels in 1 full year, moving at 300,000 kilometers per second continuously, without ever stopping or slowing down. To put this in some kind of perspective, remember that Voyager 1 has been travelling for nearly 50 years and has covered about 24 billion kilometers. 1 light year is about 400 times farther than Voyager 1 has travelled in nearly half a century. If you could drive a car at highway speeds continuously, never stopping, it would take you more than 10 million years to travel 1 light year. 10 million years. Modern humans have only existed as a species for about 300,000 years. You'd need to start this impossible road trip before humans evolved, before Homo erectus, back when our ancestors were ape-like creatures in Africa, and you'd still be driving today, still not even halfway through a single light year. But let's build up to the light, year gradually, starting with smaller units of light travel. This will help us develop an intuitive sense of the scales involved. 1 light second is 300,000 kilometers. That's roughly the distance from Earth to the Moon, 384,000 kilometers, with a bit to spare. In 1 single second, light travels far enough to reach the Moon from Earth and get about 3/4 of the way back. When astronauts on the Moon communicated with Mission Control in Houston, there was about a 1.3 second delay each way because of this distance. 1 light minute is 60 light seconds, or about 18 million kilometers. This is roughly the distance to Mercury at its closest approach to the Sun, or about 12% of the distance from Earth to the Sun. 1 light hour is 60 light minutes, or about 1.8 billion kilometers. Saturn is approximately 1 light hour from the Sun. When we look at Saturn through a telescope, we're seeing it as it was about an hour and a half ago. 1 light day is 24 light hours, or about 26 billion kilometers. This is approximately where Voyager 1 is now, after nearly 50 years of travel. It's also roughly the distance to the heliopause, where the Sun's influence ends and interstellar space begins. 1 light week is 7 light days, or about 180 billion kilometers. No human-made object has ever travelled this far. Out here, the Sun would appear as just a bright star, no longer the overwhelming presence it is from Earth. 1 light month is about 30 light days, or roughly 780 billion kilometers. At this distance, looking back at the Sun through a telescope, you'd see it as just another star among thousands, not significantly brighter than many others. 1 light year is 12 light months, 52 light weeks, 365 light days, 8,760 light hours, 525,600 light minutes, 31,536,000 light seconds. Do you see how the numbers build? Each step is enormous compared to the previous one. 60 seconds in a minute might not seem like much, but when you're travelling 300,000 kilometers per second, that 60 seconds adds up to 18 million kilometers. 60 of those minutes adds up to 1 billion kilometers. 24 of those hours adds up to 26 billion kilometers, and 365 of those days adds up to 9.46 trillion kilometers. The light year is the fundamental unit astronomers use to measure distances between stars, because stars are separated by distances measured in light years. Using anything smaller would be impractical. The numbers would be too large, too unwieldy, too difficult to work with and understand. Part 7. Our nearest stellar neighbours. Proxima Centauri is the closest star to our Sun. It's part of the Alpha Centauri system, a triple star system that includes 3 stars bound together by gravity. 2 of them, Alpha Centauri A and B, are Sun-like stars orbiting each other in a slow gravitational dance that takes about 80 years per orbit. Proxima Centauri is smaller, a red dwarf with about 1/8 the mass of our Sun and 1/7 its diameter. Red dwarfs like Proxima Centauri are the most common type of star in our galaxy. They make up about 70% of all stars, but they're so dim that none are visible to the naked eye. Every star you can see in the night sky without a telescope is either larger and brighter than our Sun, or it's not a star at all but a planet. Proxima Centauri is 4.4 light-years away. Let that settle for a moment. The closest star to us, other than our own Sun, is more than 4 light-years distant. The light you would see if you looked at Proxima Centauri through a telescope left that star more than 4 years ago. It's been travelling through space at 300,000 kilometers per second every second for more than 4 years to reach your eye. 4.24 light-years is about 40 trillion kilometers. If you tried to reach Proxima Centauri with our fastest current spacecraft, the Parker Solar Probe travelling at 192 kilometers per second, the journey would take approximately 6,800 years. Think about that time span. 6,800 years ago, humans were just beginning to develop the first civilizations. The wheel hadn't been invented yet. Writing didn't exist. The pyramids of Egypt wouldn't be built for another 2,000 years. You could have launched a spacecraft to Proxima Centauri when humans first started farming, when we first domesticated animals, when we first built permanent settlements. That spacecraft would have travelled through space for the entire duration of human civilization, through ancient Mesopotamia, through ancient Egypt, through ancient Greece and Rome, through the Middle Ages, through the Renaissance, through the Industrial Revolution, through the modern era. And that spacecraft would still be travelling today, still about 1,500 years away from reaching Proxima Centauri. This is the distance to our nearest stellar neighbour. Other nearby stars are even farther. Barnard's star, the second closest star system to Earth, is about 6 light-years away. Wolf 359 is approximately 7.9 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years distant. Epsilon Eridani, a Sun-like star that's been studied for potential planets, is about 10.5 light-years away. Vega, a prominent star in the summer sky visible from the northern hemisphere, is about 25 light-years away. Arcturus, one of the brightest stars visible from Earth, is approximately 37 light-years distant. Capella, another bright star, is about 43 light-years away. When you look at these stars, you're seeing them as they were decades ago. The light entering your eye tonight from Vega left that star 25 years ago, a quarter century ago. If you're 25 years old and you look at Vega tonight, you're seeing light that began its journey the year you were born. When that light left Vega, you didn't exist yet. Your parents might have been looking up at that same star, seeing even older light that left Vega 50 years ago. If you look at Arcturus, you're seeing it as it was 37 years ago. If you're 40 years old, you're seeing Arcturus as it was when you were 3 years old. You've lived most of your life while that light has been travelling through space to reach your eye tonight. Betelgeuse, the red supergiant star that marks Orion's shoulder, is one of the most famous stars in the night sky. It's easily visible as a bright reddish star in the winter constellation Orion. Betelgeuse is about 550 light-years away. 550 light-years. The light you see from Betelgeuse tonight started its journey in the 1470s during the Italian Renaissance. Leonardo da Vinci was 20 years old. Michelangelo was about to be born. Columbus was 19 and would sail to the Americas 20 years later. The Byzantine Empire had fallen to the Ottoman Turks 20 years earlier. The printing press had been invented about 20 years before. Most of Europe was still emerging from the Middle Ages. When that light left Betelgeuse, the world was profoundly different from today. The Americas were unknown to Europeans. The scientific revolution hadn't happened. There were no telescopes, no microscopes, no understanding of physics or chemistry as we know them today. And that light has been travelling through space for more than 5 centuries, crossing the vast distance between Betelgeuse and Earth to arrive at your eye tonight. Betelgeuse is particularly interesting because it's a massive star nearing the end of its life. Stars like Betelgeuse burn their fuel much faster than smaller stars. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will briefly shine as bright as the full moon in our sky, visible even during daylight hours. It will be one of the most spectacular astronomical events visible from Earth in human history. But here's something to think about. Betelgeuse might have already exploded. The explosion might have happened centuries ago. Maybe it happened in the year 1700, or 1800, or 1900. But we wouldn't know yet. The light from that explosion would still be travelling toward us, taking 550 years to make the journey. If Betelgeuse exploded in the year 1700, we won't see it until around the year 2250. The star could already be gone, destroyed in a catastrophic supernova, and we'd still see it shining peacefully in Orion's shoulder for decades or centuries to come, completely unaware that we're seeing a ghost, an image of something that no longer exists. This is one of the profound implications of light years. When you look at distant objects in space, you're not seeing them as they are now. You're seeing them as they were when the light left them. You're looking back in time. Distance and time become inseparable. Within about 20 light years of Earth, there are roughly 130 known star systems. 20 light years sounds like it should be a significant radius, a substantial neighbourhood. But our galaxy, the Milky Way, is 100,000 light years across. 20 light years is 0.02% of the galaxy's diameter. It's a tiny fraction, and an almost infinitesimal bubble of space around our sun. We're surrounded by stars. The night sky is filled with them, but even our closest neighbours are separated from us by distances that would take thousands or tens of thousands of years to cross with any technology we currently have or can realistically imagine developing in the near future. Part 8. The Milky Way Galaxy. Our galaxy, the Milky Way, is a spiral galaxy. If you could somehow travel far outside it and look back, you'd see a disc-shaped structure with sweeping spiral arms curving through it, like a cosmic pinwheel slowly rotating in the darkness of space. The disk would appear bright, glowing with the combined light of hundreds of billions of stars. You'd see darker lanes of dust threading through the spiral arms, regions where new stars are being born from collapsing clouds of gas and dust. At the centre of the disk you'd see a bright bulge, a dense concentration of older stars orbiting tightly around the galactic centre. And surrounding all of this, you'd see a faint spherical halo of ancient stars and globular clusters, some of the oldest objects in the galaxy, formed when the Milky Way itself was young. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is difficult to determine because we're inside the galaxy. embedded within one of its spiral arms, like trying to count trees while standing in the middle of a vast forest. Dust blocks our view in many directions, particularly toward the galactic center. Dim stars are hard to detect at great distances, and the galaxy is so large that we can only observe portions of it directly. But our best estimates, based on observations of other galaxies similar to ours, on models of galactic structure, and on surveys of the stars we can detect, suggest there are approximately 200 to 300 billion stars in the Milky Way. Our Sun is one of these stars, nothing particularly special from a galactic perspective, just a medium-sized yellow dwarf star of average brightness, not the largest, not the smallest, not the hottest, not the coolest, not the brightest, not the dimmest, just a typical star, one among hundreds of billions. Our Sun is located in one of the spiral arms called the Orion Arm or Orion Spur, about 26,000 light-years from the galactic center. 26,000 light-years. Let that distance settle in your mind. The Sun is 26,000 light-years from the center of our galaxy. Light from the galactic center takes 26,000 years to reach us. If we could see through all the dust that blocks our view, which we can't with visible light, though we can detect it with infrared and radio telescopes, we'd be seeing the galactic center as it was 26,000 years ago. 26,000 years ago, humans were living as hunter-gatherers in the Stone Age. We had simple stone tools and animal skin clothing. We were beginning to create cave art. The famous paintings at Lascaux and Altamira would be made several thousand years later. We had no permanent settlements, no agriculture, no domesticated animals except possibly dogs. We lived in small nomadic bands, following animal herds, gathering wild plants, seeking shelter in caves or simple structures. The entire development of human civilization has occurred while light from the galactic center has been traveling toward us. Agriculture was invented about 10,000 years later. Cities emerged about 14,000 years later. Writing appeared about 21,000 years later. All of recorded history, all of civilization as we know it, has happened while that light was crossing the space between the galactic center and our solar system. And that light arrives tonight, carrying an image of our galaxy's heart as it appeared in the deep past, before anything we would recognize as civilization existed on Earth. The Milky Way is roughly 100,000 light-years across from one edge to the other. 100,000 light-years. If you could travel at the speed of light, which remember is impossible for anything with mass, it would take you 100,000 years to cross from one side of the galaxy to the other. 100,000 years. Modern humans, Homo sapiens, are about 300,000 years old as a species. You could have started crossing the galaxy when the first modern humans appeared in Africa, travelled at the speed of light continuously for 100,000 years, and you'd still have 200,000 years of human existence remaining when you finish the journey. Or think of it this way. 100,000 years ago, humans were just beginning to migrate out of Africa. We were spreading into the Middle East, into Asia. We would reach Europe about 45,000 years ago, Australia about 50,000 years ago, the Americas about 15,000 years ago. You could have started crossing the galaxy when humans first left Africa, and you'd arrive at the opposite edge just about now. The entire global expansion of humanity, the entire colonization of every continent except Antarctica, all of human diversity and adaptation and cultural development would have occurred during that crossing. Our Sun, along with all the planets, asteroids, comets, and other objects in our solar system, orbits the galactic center. We're not stationary. We're moving through space, following a roughly circular path around the galaxy's center. Our orbital speed is about 230 kilometers per second, about 828,000 kilometers per hour. That's fast. At that speed, you could travel from Earth to the Moon in about 25 minutes. You could circle the Earth in about 3 minutes. We're moving incredibly fast by human standards, carried along by the galaxy's rotation, orbiting the distant galactic center. And yet, even at this tremendous speed, it takes our Sun approximately 225 to 250 million years to complete one full orbit around the galaxy. 225 to 250 million years for one orbit. This length of time is sometimes called a galactic year or cosmic year. The last time our Sun was at its current position in its orbit, the last time it was in this same location relative to the galactic center, was about 225 million years ago. What was happening on Earth 225 million years ago? Dinosaurs were just beginning to evolve. The first dinosaurs appeared about 230 million years ago, small bipedal creatures, nothing like the massive sauropods or the fearsome theropods that would come later. Since that time, since the Sun was last at this position in its orbit, dinosaurs evolved and diversified. They grew to enormous sizes. They developed into thousands of species. They ruled the Earth for more than 160 million years, dominating every ecosystem, evolving into every ecological niche. And then, 66 million years ago, a massive asteroid struck Earth, and most dinosaurs went extinct. After the dinosaurs' extinction, mammals diversified. They grew larger, more diverse. Primates evolved, apes evolved, hominids evolved, humans evolved. We developed tools, language, culture, civilization. All of recorded history occurred. All of human achievement, every empire that rose and fell, every discovery, every work of art, everything humans have ever done. And the Sun has only just now returned to approximately the same position in the galaxy where it was when dinosaurs first appeared. This is the timescale of galactic motion. The galaxy rotates, but so slowly from our perspective that we can't perceive it at all. The stars appear fixed in the sky from year to year, from century to century. Only over thousands or millions of years do their positions noticeably shift. Our galaxy is just one structure in the universe, but it's our structure, our home on the cosmic scale, and even within this single galaxy, the distances and timescales are almost incomprehensibly vast. Part 9. The local group and beyond our galaxy doesn't exist in isolation. It's part of a small cluster of galaxies called the local group, containing about 80 galaxies bound together by gravity. Most of these galaxies are small dwarf galaxies, containing millions or billions of stars, rather than hundreds of billions. But the local group also contains 3 large spiral galaxies: the Milky Way, the Andromeda Galaxy, also called M31, and the Triangulum Galaxy, M33. The Andromeda Galaxy is the nearest large galaxy to the Milky Way. On a dark, clear night, far from city lights, you can sometimes see it with the naked eye as a faint, fuzzy patch in the constellation Andromeda. It doesn't look like much without a telescope, just a dim smudge. But what you're seeing is extraordinary. Andromeda is approximately 2.5 million light-years away. 2.5 million light-years. The light you see from Andromeda began its journey 2.5 million years ago. When that light left Andromeda and started travelling toward us, humans didn't exist. Homo sapiens wouldn't appear for another 2 million years. Our ancestors at that time were early hominids like Australopithecus, barely distinguishable from other apes, walking upright but with small brains and no sophisticated tools. That light has been travelling through space for the entire duration of human evolution. It travelled while Homo habilis evolved, while Homo erectus appeared and spread across Africa and Asia, while Homo heidelbergensis emerged, while Neanderthals and Denisovans evolved, while modern humans finally appeared about 300,000 years ago. It travelled while humans developed language, while we spread across the globe, while we created art and tools and culture. It travelled through all of human history, all of prehistory, all of our evolutionary journey from ape-like ancestors to modern humans. And that light arrives tonight, entering your eye if you happen to look in Andromeda's direction. Andromeda is a large spiral galaxy, similar to the Milky Way but somewhat bigger. It contains approximately 1 trillion stars, about 4 times as many as our galaxy. Its spiral disk is about 220,000 light-years across, more than twice the diameter of the Milky Way. If you could see it clearly, if your eyes were sensitive enough, and if it weren't so far away that it appears dim, Andromeda would appear 6 times wider than the full moon in our sky. The galaxy is actually huge, but it's so distant that we can barely see it. Andromeda and the Milky Way are approaching each other. Gravity is pulling them together at a speed of about 120 kilometers per second. In approximately 4 billion years they'll collide, or rather, merge. Galaxies are mostly empty space, so the stars will pass through each other like 2 clouds interpenetrating. But the gravitational interactions will be dramatic, throwing stars into new orbits, triggering waves of star formation as gas clouds collide, eventually mixing the 2 galaxies into a single larger galaxy. But 4 billion years is so far in the future that it's almost meaningless to us. 4 billion years ago, Earth was newly formed and lifeless. Single-celled organisms were just beginning to emerge, multicellular. Life wouldn't exist for another 2 billion years. Complex animals wouldn't appear for another 3.5 billion years. 4 billion years is longer than complex life has existed on Earth. For now, for the foreseeable future, Andromeda remains 2.5 million light-years away, a separate galaxy, a separate island of stars in the cosmic ocean. The Triangulum galaxy, the 3rd large member of the local group, is about 3 million light-years away. It's smaller than the Milky Way or Andromeda, containing perhaps 40 billion stars, but it's still a substantial galaxy. Beyond the local group we encounter other galaxy clusters. The nearest large cluster, the Virgo cluster, is about 55 million light-years away and contains more than 1,000 galaxies. The Coma cluster is about 320 million light-years away and contains thousands of galaxies. The Hercules cluster is about 500 million light-years distant. At these distances, we're seeing these galaxy clusters as they were millions of years ago. When we observe the Virgo cluster through our telescopes, we're seeing it as it was 55 million years ago. The dinosaurs had been extinct for 11 million years. Mammals were diversifying and spreading across Earth. The ancestors of horses, whales, and primates were evolving, and the light from the Virgo cluster was beginning its journey across space, travelling for 55 million years to reach our telescopes today. When we look at the Coma cluster, we're seeing it as it was 320 million years ago, before dinosaurs even existed, when the Earth's continents were joined in the supercontinent Pangaea, when the dominant land animals were early reptiles and amphibians. At the largest scales, galaxies aren't randomly scattered through space. They're organized into structures. Galaxy clusters are grouped into superclusters, massive structures containing dozens or hundreds of galaxy clusters. Our own local group is part of the Virgo supercluster, also called the local supercluster, which contains about 100 galaxy clusters and spans about 110 million light-years. But even superclusters aren't the largest structures. Observations have revealed that superclusters are arranged in filaments, enormous thread-like structures stretching hundreds of millions of light-years across space. Between these filaments are vast voids, enormous regions containing very few galaxies, empty spaces that can be 200 to 300 million light-years across. The universe has architecture. It has structure on the largest scales imaginable, and all of it is measured in light-years, in millions or billions of light-years, distances so vast they make our entire galaxy seem small by comparison. Part 10. The Observable Universe. The universe is approximately 13.8 billion years old. We know this from multiple lines of evidence. The expansion rate of the universe, the cosmic, microwave background radiation, the afterglow of the Big Bang, the ages of the oldest stars, and the distribution of elements in space. All of these point to a universe that began about 13.8 billion years ago. Since the Big Bang, light has been travelling through space. Over the past 13.8 billion years, light has been propagating outward from distant regions, carrying information about those regions to us. The farthest we can possibly see is limited by the age of the universe and the speed of light. But there's a complication. The universe has been expanding since the Big Bang. Space itself has been stretching, carrying galaxies apart from each other like raisins in rising bread dough. This expansion affects how far we can see. While light from distant galaxies was travelling toward us, space was expanding, increasing the distance between us and those galaxies. This means the edge of the observable universe, the most distant point from which light has had time to reach us, is not 13.8 billion light-years away. It's much farther. The edge of the observable universe is approximately 46.5 billion light-years away in every direction. This makes the observable universe roughly 93 billion light-years in diameter. 93 billion light-years. This is the size of the region of space we can potentially observe, the region from which light has had time to reach us since the beginning of the universe. Beyond this distance, space has been expanding so fast that light from those regions hasn't reached us yet and may never reach us. Within this observable universe, there are an estimated 2 trillion galaxies. 2 trillion, that's 2,000 galaxies. Each galaxy contains billions or hundreds of billions or even trillions of stars. Each star might host planets. The numbers become almost incomprehensible. If we estimate conservatively that each galaxy contains an average of 100 billion stars, though many contain far more, then the observable universe contains about 200 billion trillion stars. That's roughly 200,000 stars, 200 sextillion stars. And recent observations suggest that most stars host at least one planet. So there are probably at least as many planets as stars, possibly many more. The universe is filled with worlds, more worlds than we could ever count, more worlds than we could visit if we had billions of years and could travel at the speed of light. The universe is unimaginably vast, and all of it is measured in light years. All those distances between stars, between galaxies, between superclusters, all the cosmic architecture stretching through space. Part 11. The Implications for Human Existence. We've travelled from the familiar distances of our daily lives, the walk to the park, the drive to another city, to the almost inconceivable distances of the cosmos. 2.5 million light-years to Andromeda, 93 billion light-years to the edge of the observable universe. This journey has implications for how we think about our place in the universe, about the possibility of space exploration, about the likelihood of contact with other civilizations. The speed of light is not just fast, It's the ultimate speed limit of the universe. According to our best understanding of physics, based on Einstein's theory of special relativity, and confirmed by more than a century of experiments and observations, nothing with mass can reach the speed of light. This isn't a technological limitation we might overcome with better engineering or more powerful rockets or some future breakthrough. It's a fundamental law of nature. As objects approach the speed of light, their mass effectively increases, or more precisely, their inertia increases, their resistance to further acceleration increases. The energy required to continue accelerating them grows without limit. To actually reach the speed of light would require infinite energy, which is impossible. This means the distances measured in light years represent real fundamental barriers. A star that's 10 light years away is separated from us not just by space, but by time. Even if we could travel at the speed of a light, which we can't, it would take 10 years to reach that star. We'd arrive 10 years older. Everyone we knew on Earth would be 10 years older. 10 years would have passed, and we can't travel at the speed of light. With our current technology, interstellar travel would take thousands or tens of thousands of years. To make it practical would require revolutionary breakthroughs, perhaps some way to accelerate spacecraft to a significant fraction of light speed, perhaps some form of suspended animation to keep crews alive during centuries-long journeys. Even in the most optimistic scenarios, even assuming breakthrough propulsion technologies that let us accelerate to, say, 10% of light speed, a journey to Proxima Centauri would take more than 40 years. That's longer than most careers, longer than the typical span from graduation to retirement, and that's just to reach the nearest star. Most stars are much farther away. Most destinations of interest, planets that might harbour life, stellar systems with unusual properties, regions of recent star formation, are dozens or hundreds of light years away. Journeys to these destinations would take centuries even at 10% of light speed. Communication across light years faces similar fundamental barriers. Radio waves, like light, travel at 300,000 kilometers per second. They're both electromagnetic radiation, just at different frequencies. A radio signal traveling to a star 10 light years away takes 10 years to arrive. A reply takes another 10 years to return. That's a 20-year round trip for a single exchange of messages. For more distant civilizations, communication becomes almost absurd. A civilization 100 light years away would have a 200-year communication delay. You'd send a message, and your great-great-great-grandchildren might receive the reply. The conversation would span generations. Each generation would be responding to messages sent by people who died decades or centuries earlier. Think about what this means for the search for extraterrestrial intelligence. Given the vast number of stars and planets, given that life arose on Earth relatively quickly after conditions became suitable, it seems likely that life has arisen elsewhere. Perhaps many times, perhaps even intelligent technological life. But if civilizations are separated by dozens or hundreds of light years, communication becomes extraordinarily difficult. You'd need to detect extremely faint signals that have been traveling for decades or centuries. You'd need powerful transmitters to send replies that would take decades or centuries to arrive. You'd need civilizations that remain stable and interested in communication for centuries or millennia. And these are optimistic assumptions, assuming civilizations only dozens or hundreds of light years apart. If the average distance between intelligent civilizations is thousands of light years, as seems quite possible given how rare intelligence might be, then communication becomes essentially impossible. By the time signals travel that far, civilizations might rise and fall. The civilization that sent a signal might be gone by the time any reply arrives. This creates a somewhat lonely picture of the universe. It might be filled with life, perhaps even intelligent life, but that life is separated by distances so vast that contact is difficult or impossible. Each civilization develops in isolation, makes its discoveries alone, asks its questions alone, never knowing if others are out there, never able to share knowledge or culture or history with beings under other suns. There's something melancholy about this realization. We've evolved as social creatures. Connection is fundamental to who we are. We build communities, share knowledge, collaborate on projects. The idea of being alone in the universe, or of being surrounded by others but unable to reach them because of the light years between us, is profoundly isolating. But there's also something beautiful about it. It means every civilization that arises is precious. Every occurrence of intelligent life, every consciousness, every being that can look up at the stars and wonder about them, each is unique, valuable, irreplaceable. If we're alone, or effectively alone because we can't reach anyone else, then we carry a unique responsibility. We're the universe's way of knowing itself in this corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us, happening here and now and perhaps nowhere else for dozens or hundreds of light years in any direction. Part 12. Looking backward in time. One of the most profound aspects of light years, one we've touched on several times but which deserves deeper consideration, is how they connect distance and time. When you look at a star 10 light years away, you're seeing it as it was 10 years ago. The light entering your eye right now left that star a decade ago. This isn't just an interesting fact, it's fundamental to how we observe and understand the universe. Astronomy is inherently the study of the past. We can never observe the universe as it is right now in its entirety. We can only observe it as it was at various times in the past, depending on the distance to what we're observing. When astronomers point their telescopes at distant galaxies, they're looking backward in time. A galaxy 1 million light years away appears to us as it was 1 million years ago. A galaxy 1 billion light years away appears as it was 1 billion years ago. The light has been travelling across space all that time, and what we see is ancient history. The farther we look in distance, the farther we look in time. The most distant galaxies we've detected are more than 13 billion light years away. We're seeing them as they were more than 13 billion years ago when the universe was very young, only a few 100 million years old. We're seeing galaxies forming, the first stars igniting, the first heavy elements being created. In a very real sense, telescopes are time machines. They don't let us travel through time physically, but they let us see the past. They let us observe the universe at different epochs, watching the story of cosmic evolution unfold as we look at increasingly distant objects. This also means we can never see the universe as it is right now in its entirety. We can only see the observable universe, the region from which light has had time to reach us. Our view of the universe is inherently historical. What we see is a patchwork of different times, nearby stars as they were years ago, distant stars as they were decades or centuries ago, nearby galaxies as they were millions of years ago, distant galaxies as they were billions of years ago. There's no way to take a snapshot of the universe right now across all distances. The very concept doesn't make sense given the finite speed of light. Right now is different depending on where you're looking. Every time you look up at the night sky, you're looking at history. Each star's light has been travelling for years or centuries or millennia. You're seeing a collection of different moments from the past, all arriving at your eye at the same time. Sirius, the brightest star in the night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. You're seeing Sirius as it was when you were 8.6 years younger, when you were living a different life, perhaps in a different place, with different concerns and hopes. Polaris, the North Star, is about 445 light-years away. When you look at Polaris tonight, you're seeing light that began its journey in the late 1500s. When that light left Polaris, Shakespeare was just beginning to write his plays. The first permanent English colonies in North America hadn't been established yet. The telescope hadn't been invented. Most of the world was unmapped by Europeans, and that light has been travelling through space ever since, crossing the vast distance between Polaris and Earth to arrive at your eye tonight. Everything you see in the past. Even when you look at something across the room, you're seeing it as it was a few nanoseconds ago, billionths of a second ago. The delay is usually far too small to matter, but it's always there. Light always takes time to travel, even if that time is infinitesimally small for everyday distances. But for astronomical distances, the delays become significant. Minutes for objects in our solar system, years for nearby stars, centuries for distant stars, millions of years for nearby galaxies, billions of years for the most distant galaxies. This temporal aspect of observation has practical implications for astronomy. When astronomers study the evolution of the universe, they're not making assumptions or guesses. They're literally looking at the universe at different ages. By comparing nearby galaxies, which we see as they were in the relatively recent past, with distant galaxies, which we see as they were billions of years ago, we can watch galactic evolution happening. We can see how galaxies have changed over cosmic time. When we study the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, we're observing the universe as it was about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space for the first time. That light has been travelling for 13.8 billion years to reach us, carrying information about the infant universe. The universe itself is a historical archive. Every photon is a messenger from the past. Every observation is a window into history. The distances measured in light years are also measures of time, of how far back we're looking into the universe's past. Part 13. The Human Scale Reconsidered. Throughout this long contemplation, we've moved from the intimate distances of our daily lives to the almost incomprehensible scales of the cosmos. It's worth pausing now to bring things back to human scale, to consider what all of this means for us as individuals living our lives on Earth. The light year doesn't change your immediate experience of the world. Tomorrow, you'll wake up in a familiar place. You'll move through rooms you know. You'll travel distances measured in meters and kilometers, not light years. Your daily life operates at human scales, and those scales work perfectly well for everything you need to do. The grocery store is still a few kilometers away. Your home is still a comfortable, walkable space. The people you love are accessible to you. The world you interact with directly is human-sized, human-paced, human-scaled. But knowing about light years, understanding the true scale of the universe, can shift your perspective in subtle and meaningful ways. When you look up at the night sky on a clear evening, you're no longer seeing just pretty points of light. You're seeing distant suns, each one potentially hosting its own system of planets and moons. You're seeing across vast expanses of space and time. You're receiving light that has been travelling for years or centuries or millennia, photons that have crossed unimaginable distances to reach your eye. You're witnessing the universe in its immensity. There's something deeply humbling about this. Your entire life, all your experiences, all your worries and joys and struggles and triumphs, they occur on one small planet orbiting one ordinary star in one average galaxy among trillions. From the cosmic perspective, you're infinitesimally small, brief, localized. Your life is shorter than a single cosmic heartbeat. When you're stressed about work, about relationships, about money, about health, these concerns feel enormous. They fill your awareness. They seem all-consuming, and they are real. They matter to you, and that makes them important. But from the perspective of the stars, from the perspective of the galaxy, from the perspective of the universe with its 93 billion light-years of observable space and its 13.8 billion years of history, your concerns are tiny, temporary, local. They exist for a brief moment on one small world. They don't echo through the cosmos. They don't disturb the stars. This perspective doesn't diminish your experiences. It doesn't make your life less meaningful, but it can provide comfort when things feel overwhelming. Your problems are manageable precisely because they're human-scaled. They're temporary. They'll pass. The universe continues its slow evolution, utterly indifferent to human concerns, and somehow that indifference can be reassuring. There's also something empowering about understanding our place in the cosmos. We're part of this vast universe. We're made of atoms that were forged in the hearts of stars that died billions of years ago, scattered through space when those stars exploded, eventually gathered into clouds of gas and dust that collapsed to form our solar system, our planet, and ultimately us. You're literally made of stardust. Your body contains carbon, nitrogen, oxygen, iron, calcium, all elements that were created in stellar furnaces and scattered through space by supernova explosions. You're a temporary arrangement of cosmic material that happens to be conscious, that happens to be capable of looking up at the stars and understanding what you're seeing. The fact that we figured any of this out's remarkable. We're small creatures on a small planet with lives that last only decades, and yet we've measured distances to galaxies billions of light-years away. We've determined the age of the universe. We've mapped the cosmic structure of space. We've understood our place in the vastness. We built telescopes and spacecraft. We developed mathematics and physics. We learned to read the light from distant stars, extracting information about their composition, their temperature, their motion, their age. We're capable of extraordinary things despite our small size and brief existence. Part 14. The continuing exploration. Our understanding of the universe continues to evolve. New telescopes see farther and more clearly than ever before. The James Webb Space Telescope, launched in late 2021, can detect infrared light from galaxies more than 13 billion light-years away, showing us the universe as it appeared in its first few 100 million years. We're discovering exoplanets at an accelerating rate. As of the mid-2020s, we've confirmed more than 5,000 planets orbiting other stars, with thousands more candidates awaiting verification. These planets are scattered throughout our region of the galaxy at distances ranging from a few light-years to thousands of light-years. We've found planets similar in size to Earth, planets in the habitable zones of their stars where liquid water might exist on their surfaces, planets orbiting in systems very different from our own. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets, orbiting a small red dwarf star. 3 of these planets are in the habitable zone. When we observe this system, we're seeing it as it was 40 years ago, in the mid-1980s. If there's life on any of those planets, if that life is advanced enough to have developed radio technology, and if they're broadcasting signals into space, those signals would take 40 years to reach us. We might detect them decades from now, messages from the 1980s arriving in our future. We're mapping the structure of our galaxy in unprecedented detail. The Gaia spacecraft has measured the positions and distances of more than 1 billion stars, creating the most precise three-dimensional map of our galactic neighborhood ever made. We're learning about the Milky Way's structure, its spiral arms, its rotation, its history. We're studying the large-scale structure of the universe, the filaments and voids, the distribution of galaxies across cosmic scales. We're measuring the expansion rate of the universe, trying to understand the mysterious dark energy that's accelerating that expansion. We're looking for signs of dark matter, the invisible substance that makes up most of the matter in the universe. As our instruments improve, as our techniques become more sophisticated, we'll see farther, measure more precisely, understand more deeply. We'll continue mapping what exists at these vast distances, continue exploring the universe through our telescopes and spacecraft, even though we may never be able to physically travel to most of the places we study. The light year will remain our fundamental tool for measuring cosmic distances. It's elegantly simple, just the distance light travels in 1 year, and yet perfectly suited to describing the vast scales of space. It's based on a universal constant that never changes. It provides a way to compare relative distances without losing track of the scales involved. And it inherently reminds us that distance and time are connected, that in the cosmos, where something is and when we observe it, are inseparably linked. As we discover galaxies farther and farther away, as we look deeper into the universe's past, as we continue our exploration of the cosmos, the light year will be there as our measuring stick, our standard, our way of making sense of distances that dwarf anything in human experience. Part 15. A gentle closing meditation. We've travelled far together tonight, from the familiar distances of our everyday world to the cosmic scales where light needs billions of years to cross space. We've built up gradually, step by step, from kilometers to light seconds to light years to millions and billions of light years. A light year is 9.46 trillion kilometers. It's the distance light travels in 1 year, moving at 300,000 kilometers every single second, continuously, without ever stopping or slowing down. It's a distance almost impossible to comprehend intuitively, but we can understand it conceptually. We can work with it. We can use it to map the universe and understand our place within it. The nearest star to our sun is more than 4 light years away. Our galaxy is 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years distant. The observable universe stretches more than 90 billion light years from edge to edge, containing 2 trillion galaxies, each with billions or trillions of stars. These are the distances that define our universe. They're vast beyond easy comprehension, but they're real, measurable, knowable. We figured them out. We measured them. Despite being small, creatures on a small world, we understood our place in the cosmic expanse. When you look up at the stars tonight, remember what you're seeing. Those points of light are distant suns, separated from us by distances measured in light years. The light entering your eye has been travelling across space for years, or decades, or centuries. You're seeing across vast expanses of space and time, connected to those distant stars by photons that have crossed the cosmic void to reach you. Each photon is a messenger. Each one has made an incredible journey. traveling at the speed of light through the emptiness of space for years or centuries, carrying information about a distant sun, finally ending its journey by entering your eye and being absorbed, its energy converted to electrical signals in your retina, interpreted by your brain as light, as a star, as wonder. The universe is larger than we can fully grasp, but we're part of it. We're here on this small planet, safely orbiting our sun, looking out at the cosmos and beginning to understand what we see. We're conscious matter, the universe's way of knowing itself, of contemplating its own vastness and beauty. There's something peaceful about this knowledge. The universe is vast, ancient, mysterious. But you're here within it, part of its structure, part of its story. Your life is brief on cosmic timescales, but it's your life, real and meaningful and precious. You matter, even in a universe 90 billion light-years across, even in a universe 13 billion years old. The stars are far away. The distances between them are so vast they challenge our ability to comprehend. But every time you look up at them, you're participating in something ancient and profound. Humans have looked at these same stars for thousands of years, wondering about them, telling stories about them, eventually learning to measure the distances to them. You're part of that story. You're living at a time when humanity has figured out how far away the stars are, how large the universe is, how long light takes to cross cosmic distances. You're living at a time when we can look back nearly to the beginning of the universe itself, seeing galaxies as they were billions of years ago. Rest now in this knowledge. Let your breathing slow. Let your body relax. The universe is vast, but you're safely here on Earth, under the same sky that has arched over humanity since our beginning. The distances we've explored tonight are real, but they're also abstract, mathematical, conceptual. They don't threaten you. They don't change the immediate reality of your comfort, your safety, your peace. The stars will continue shining, their light crossing light years of space to reach Earth. The galaxies will continue their slow dance through the cosmos. The universe will continue its expansion, its evolution, its vast and patient unfolding. Time will pass on cosmic scales, millions of years, billions of years, but here on Earth now, in this moment, you're safe and warm and alive. You're made of the same atoms as the stars. You follow the same physical laws. You're connected by gravity and light to everything in the universe, from the closest atoms in your body to the farthest galaxies at the edge of the observable universe. You're part of the cosmos, not separate from it. The universe isn't out there, it's everywhere, and you're within it, made of it, part of its ongoing story. The light year is more than a measurement. It's a tool that lets us comprehend distances far beyond human experience. It's a way of making sense of the vast scales of space. It's a reminder that distance and time are connected, that in the cosmos, where something is, and when we see it, are inseparably linked. But it's also a reminder of something deeper, that the universe is knowable, that we, small as we are, brief as our lives are, can understand cosmic scales, that we can look up at the night sky and truly grasp what we're seeing, that we're capable of measuring distances our bodies could never cross, of comprehending timescales longer than human existence, of understanding our place in the vastness. Sleep well tonight, knowing you're part of this vast cosmos. Dream peacefully of stars whose light has travelled for years to reach your eyes. Rest in the knowledge that the universe is large beyond measure, ancient beyond comprehension, but you're here within it, safely cradled on this small world, connected to everything through the fundamental forces that bind all matter and energy together. The light will continue its eternal journey across the years. The stars will keep their distant vigil, and you'll wake tomorrow to a new day under the same vast sky, carrying perhaps a deeper sense of the cosmic scales that surround our small, warm, living world. The nearest star is 4 light-years away. The farthest visible galaxies are 13 billion light-years distant, and you are here now in between, a conscious being capable of understanding both distances, of holding both scales in your mind simultaneously. That's extraordinary. That's precious. That's worth celebrating, even as you rest, even as you let go of the day, even as you drift towards sleep. The stars are shining light years away, and you are here, connected to them across the vast distances by the gentle, constant flow of light through space. Everything is as it should be. The universe is unfolding as it always has, vast and patient and beautiful. The cosmos continues its dance, and you're part of it, safe and small and infinitely valuable.